how to determine crystal lattice energies using what's called a Born-Haber cycle. Haber, very famous German chemist, came up with the Haber process for converting nitrogen from the air into ammonia to be used as fertilizers. Revolutionized the field of fertilizers and explosives, unfortunately. But here he is, he's immortalized. The Born-Haber process. Start with elements in their lowest energy state and turn them into gaseous ions. This is a very much a process, and what I'm going to do is we're going to do a very large version of Hess's law, and we're going to build the reaction not for the crystal lattice energy, but instead for delta H formation of sodium chloride solid. And delta H formation, that reaction is going to be sodium solid plus half chlorine gas goes to sodium chloride solid. And this is what's called a delta HF, or formation reaction. It forms the sodium chloride solid out of the lowest energy forms of its elements, sodium and chlorine. And the value here is going to be minus 411 kilojoules per mole. And this will be given, but you will be expected to know how to write a formation reaction for anionic compounds. Although you could also do it for non-ionics as well. Mostly ionics. Okay, so now what it says is these two are the lowest energy forms of each of the elements. And let's start with sodium. And it says start with the elements in their lowest energy state and turn them into gaseous ions. Well, first we'll turn them into gases. Sodium solid going to sodium gas. That is the sublimation process. So delta H sublimation for sodium. And again, this is a value that would have to be given to you. I have to look it up. 108 kilojoules per mole, where I don't need my units because all of these numbers will be in kilojoules per mole. Now, a sodium ion is typically seen with a +1 charge. So we will then take our sodium gas, turn it into a sodium ion gas. That takes away 1 electron, which will be the other product. This is a reaction we've seen before, and all of these will be reactions that are pretty familiar to us, or at least we've seen them before. So this is going to be delta H ionization energy, and it will be IE1, meaning the first ionization energy for sodium. That value is given as 496 kilojoules per mole. And we're, believe it or not, we're done with that. We'll come back to it in a minute. Now we're going to take chlorine in its lowest energy state and turn it into gaseous ions, and only doing reactions that we know or have seen before. And we haven't seen this reaction with a half, but we have very recently seen chlorine molecule becoming atoms. That was the bond dissociation energy. For a chlorine-chlorine single bond, and we said that was 242 kilojoules per mole. And we'll talk about adjusting coefficients in a minute. Now we have chlorine gas atoms. To turn a chlorine gas atom into a Cl-, that is an electron affinity reaction. we didn't have to know trends in electron affinity, but we did have to know how to write an electron affinity reaction. That is delta H electron affinity 1 for chlorine. And again, these numbers are all provided. This is minus 349 kilojoules per mole. Provided in the problem statement or on our conversion and equation sheet in the case of the bond association energy. Well, again, this is a process, and we now have created sodium gas ion and chloride gas ion. And the last one is what we identified earlier as the crystal lattice energy. And it is the only part of this massive Hess's law called the Born-Haber cycle that we don't know. And it goes like this: sodium gas ion plus chloride gas ion becomes sodium chloride solid. And that is our X. We don't know it. And it's the only one we don't know. So when we add up all 5 of these reactions, a la peanut butter sandwich, a la Hess's law, we get this bottom reaction here, which means we may likewise add all, wait, not quite, hold on, Bill. It doesn't match. We have a half Cl2 here, and we have a Cl2 here. So let's multiply this reaction times half. And when we do that, we multiply the delta H value times half. Now that gives us 1 Cl, 1 Cl, 1, yes. Now, everything in this reaction except, so it's a perfect Hess's law. It's a thing of beauty, actually. So the only 2 things that don't cancel on the reactant side are in our bottom reaction here. And the only thing that doesn't cancel on our product side is our 1 product. Now to add everything up, we've got 108 plus 496 plus half of 242 minus 349 plus X equals minus 411. That's a minus 411 there. Can you see that? That's a minus 411. And we're back to the Algebra Olympics again, where we add up everything and solve for X. So let's see. I'm going to add up everything on this side. It's going to be 108 plus 496 plus 242 divided by 2 minus 349. I get 376 plus X equals minus 411. Subtract 411, so subtract 376 from both sides. I get 411 minus 376. I get minus 787 kilojoules per mole, and that is the crystal lattice energy for sodium chloride. That is also our estimate of the ionic bond strength for sodium chloride as well. So it's the crystal lattice energy, and why do we care? Extreme zoom. It is our estimate of the ionic bond strength. And we'll say of the sodium chloride ionic bond strength. Because we can't do this process, we cannot take gaseous sodium and chloride ions and bring them together to make sodium chloride solid. That's why we need Hess's law. And it's turned out to be relatively useful for estimating ionic bond strengths.